Hello. In this one video, I hope to get through assigning aromaticity to these four ring molecules. They're all small rings, and they all have charges. So some are a little more difficult than others, but as we go through these examples, you'll pick up tips and things to watch out for when looking at aromaticity. So the first one is cyclopentadiene cation, and if I draw it out, we all know that a carbocation has 3 bonds and no lone pairs. Now, the first rule that we'll mention here is that rings of 5 atoms or less are too small to bend out of plane. We all know that a triangle, those 3 points always make a flat surface. We know that a square is bigger and can bend a little bit, but it can't bend out of the plane significantly enough to break conjugation. So let me put here to break. The classic example of a molecule that can bend out a plane is the cyclooctatetrene. Because if this was flat, this would be antiaromatic. But in class, we saw that just like a molecule can conform to a more stable staggered conformation than eclipsed, well, this ring could also conform to a bent conformation rather than a flat to avoid being antiaromatic. But, so we would think it's antiaromatic because it has 8 pi electrons, and right now it looks flat, but in real life, it will bend out a plane, and one way to draw that is this way. Okay, what that does is that it sufficiently breaks conjugation between the pi bonds, because now our p orbitals are not aligned. You know there's a p orbital here, but now when we kind of bend out a plane, there's enough misalignment that we don't have conjugation. And we know from our rules that if not flat, in this case, the molecule is non-aromatic. And that is the answer for this stop sign. Okay, I did not mean to go over that because a lot of you know this already, that this stop sign is non-aromatic. But again, if you go down to 5 atoms or less, you cannot bend like this 8 atom ring enough to break conjugation. So we have already one fact about this ring, and it is flat. Let me put it in blue. No, let me put it in dark blue. No, let me put it in light blue. It is definitely flat. The next thing that I would look at is, are all the atoms sp2 hybridized? Well, yes, all atoms in the ring are sp2 hybridized. So here's another phrase that you want to memorize. Carbocation carbons are always sp2. sp2 hybridized. Okay, and that is one of the requirements for aromaticity. The strategy here actually is I'm trying to see if it's aromatic, and I'm checking off the rules 1, 2, and 3, And then if it's not, then fine. We have to decide whether it's non-aromatic or anti-aromatic. Right now, we're headed towards aromaticity. Look at this. How many pi electrons are there? There are no lone pairs here on this sp2 atom, but this sp2, this sp2, this sp2, this sp2, they each have one electron in a p orbital. The p orbitals are part of the pi system. So yes, there are now there are 4 pi electrons. Okay, I thought we were headed towards aromaticity, but because there are 4 pi electrons, and because this is flat and all the atoms are sp2, this is definitely anti-aromatic. 4 pi electrons is a non-Huckel number. So this is anti-aromatic. Now, it cannot do the trick that this molecule can do. We thought it was going to be anti-aromatic, but it could bend out a plane to become non-aromatic. Because of this rule here, it's stuck at being anti-aromatic. Okay. Let's take a look at the next one. This is going to be like a 2-pager set of notes, I think. Now, the anion, we all know that anions also have the carbon. Anion has 3 bonds, but it has a lone pair. And this is where it gets a little bit tricky. Okay? First of all, we know for a fact that this is going to be considered flat. Okay? Now, would I say it's perfectly flat? No. 5 atoms, you can kind of pucker it or, lift up one corner. But so it's not perfectly flat. It's flat enough so that there is conjugation, and that rule for aromaticity, I think I had it as rule number 1, the ring is considered flat. Okay, so same thing here, the ring is considered flat. Now here's the deal. Right now, there are 4 pi electrons, and those are from the pi bonds. But it could be 6 because of resonance. And the resonance I'm talking about is this. Okay, and so which is it? Which do we want? Well, what do you want, right? You get to choose. So this is the deal. I'm gonna try to. I've tried this for several years, and I still don't think I've had the perfect wording for this kind of situation. But let me try it here. If there is an sp3 atom in the ring, but it can use a lone pair in resonance and act like an sp2 atom. Okay, this is going to be a long phrase. And so I'm still not done with that, but let me show you the result and why I think now it could be an sp2 atom. Because now that atom has a pi bond there, and now your charge is here. But I'm still looking at this particular hydrogen right here. Okay, so that carbon is now sp2 when I draw this resonance structure. So that's what I mean by if there's an sp3 atom, right? In organic chemistry 1, we thought of this as sp3 because it has 4 balloons or 4 electron domains, and it's part of the ring, but it can use a lone pair, so it has to have a lone pair in resonance and act like an sp2 atom. And here's the kicker. Consider it sp2, if beneficial. So that's the weird disclaimer. So if I kept it sp3, it would have 4 pi electrons. If the C negative charge stays sp3. But if I make it sp2, then that lone pair is part of the pi system. If consider the C minus sp2, and again, the lone pair is now part of the pi system. Not and, but the result is, therefore, the lone pair is part of the pi system. We'll have many more times to practice this. This is our first instance where it seemingly the atom can choose whether it wants to be sp3 or sp2. By the way, that makes this rule super important because you want to simplify your task. If you see a carbocation, it's always sp2. There's no choosing. It's this type of situation where you do have to choose. And it is beneficial because this is aromatic. This is a Huckel number. So I'm going to say that A, it's flat. B, all atoms of the ring are sp2. And now we have, since the lone pair is part of the pi system, we have 6 pi electrons. We got to a state where this is aromatic. And that's our final answer. Aromatic. So this cyclopentadiene anion is aromatic. This cyclopentadiene carbocation is antiaromatic. Okay? Are you hearing what I'm saying? So both of these are a cyclopentadiene ion. Cation and anion. Okay. Now here's the thing. You could draw this, okay? And you could kind of prove that the lone pair is part of the pi system if that carbon is sp2 hybridized. And I'll show you in this case. Draw it like this. And this carbon way on the right, we're going to make it the negative. So it's going to have the lone pair. So if you think about your other 4 carbons, again, what we're saying here is that let us consider this. Consider the C minus anion sp2 hybridized. You know sp2 atoms have a p orbital. So there are your p orbitals. I'm not going to label everything. We have a pi bond here between these 2 carbons. We have a pi bond here between these 2 carbons. And what do I do here? Well, I told you that the lone pair, now that it's in an sp2 atom, that lone pair is part of the pi system. And yes, in that p orbital, I'll label all of them. In that p orbital for the C anion, you do have that lone pair. And so now if I ask you how many pi electrons are in the pi system, for sure you can tell me that there are 6 pi electrons in the pi system. A Huckel number 6. Okay? Now, are there going to be examples where this is not beneficial? Then if it's not beneficial, meaning that if you change it to an sp2 atom and it becomes anti-aromatic, forget it. Go back to being sp3. Now, before we go to the next example, because this rule we'll see again later, this situation occurs when you have an atom with a lone pair that could be part of the pi system. Whether you consider that sp3 or sp2. And then you have to decide, well, am I going to get a Huckel number if I include that lone pair? Okay, let's take a look at the last two. Which one's the easier one? The easier one is, definitely this one. You know why I say that's easy? Because again, the carbocation carbon is always sp2. So all atoms in that ring are sp2. The other thing is that 5 atoms or less in a ring, always flat. See, we're trying to find things that we know for sure. Always sp2, always flat. And here we have no lone pair, so we don't have to decide if that lone pair is part of the pi system or not. We have one pi bond, there are 2 pi electrons. Ding, 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 ding. We have aromatic. 2 is a Huckel number. Okay? So here's I mentioned this on page 1. That anion is one of the most controversial assignments in aromaticity. These are called, again, cyclopropene ions. And it's the anion that's controversial. So let's take a look at that. Here's your H. Here's your negative, and here's your lone pair. Okay, this is the situation where we could choose, because we have, let me write it down. We have an sp3 atom, supposedly, right? That can put its lone pair, or let's say a lone pair, in the pi system. So we have to decide, okay, if, consider it sp3, then that molecule is what? Well, we have an sp3 atom, and that breaks one of the rules for aromaticity. So if we consider it sp3, then the molecule is non-aromatic. Remember, for it to be aromatic or anti-aromatic, all the atoms of the ring have to be sp2. And we had that. You know, we could have said that this atom is sp3 and say non-aromatic. But we realized if that lone pair is part of the pi system, we have 6 pi electrons, and we have this picture, the molecule is truly aromatic. And it's true. That molecule has very good stability. Let's take a look at this one. So that's if the atom is sp3. But if we consider it sp2, that lone pair is part of the pi system. Okay? And we see that because now that carbon is now sp2. You see that? That carbon is sp2. This carbon right here. And, well, if we're going to include the lone pair, because it's sp2, we include lone pair. We get 4 pi electrons. Ouch. 4 is an anti-Huckel number, or a non-Huckel number. It will be anti-aromatic. So in these cases where the molecule supposedly can choose, and I use the word choose lightly, the molecule knows, right? Just like with chair conformations are more stable than non-chair conformations. Well, the molecule can feel that. The molecule knows when there's strain. Okay, same thing here. The molecule knows or can feel that it is unstable and it will find a more stable situation. Guess what? The more stable situation is here. Not this one. Not anti-aromatic. So in this case, this is tricky because here we're going to keep it as sp3. The conclusion here also is that the molecule is non-aromatic and the lone pair is in an sp3 orbital. Do you see how that is different than before? Look over here. Here, the lone pair is in a p orbital because we want it to be part of the pi system. This is good. We want it to be part of the pi system because it is, again, aromatic. Okay? So we don't have this picture for the three-membered ring anion because it is sp3 hybridized. What picture do we have? I don't know. We have this picture here. You have a p orbital here, p orbital here, for those two carbons here and here that are sp2 hybridized. And I do not want to add 2 more electrons to get up to 4 pi electrons. I do not want 4 pi electrons. So I'm going to make sure that the lone pair is not part of the pi system by keeping this carbon actually sp3 hybridized. So this carbon will stay sp3, and your electrons are here. One there to make a sigma, one there to make a sigma, one there to connect with H, right, you have an H right there. And your lone pair, our conclusion is in an sp3 orbital. It takes practice, and this, I said this was controversial. Take a look at this article or this abstract from the Journal of Organic Chemistry from 2013. Read the highlight. A central idea in organic chemistry for the past 50 years is that cyclopropenyl anion is anti-aromatic. What did we just say? We said that it is non-aromatic, okay? Because we want to keep that carbon sp3 hybridized. This is a beautiful paper, and it refuted a widely held belief that this molecule right here, the three-membered ring with the anion, was anti-aromatic. But through computational studies, this professor, showed that it's really non-aromatic, and it falls with other non-aromatic molecules, where that carbon is what? That carbon is sp3 hybridized. Okay, if you're making note cards, the first one, anti-aromatic. Second one, this one here, aromatic. Okay, it doesn't matter which one you draw. Know how to draw the orbital picture to prove that we want that lone pair part of the pi system. The third example, clearly aromatic. That was one of the easier ones. Let me double check. Yeah. What was the 5-membered ring plus anti? Okay, good. And then the last one, the controversial one, let's keep this sp3. Because if we include the lone pair, we would bump up to 4 pi electrons, which would make it anti-aromatic. So let's not do that. Let's keep it sp3. Let's make the lone pair in an sp3 orbital and make it non-aromatic. Non-aromatic is a much better situation, much more stable situation for a molecule than being anti-aromatic.